All right, so we are on to testing means. This is section 10.3. When we test a mean, we're going to use the following. We can use the following steps, assuming the following. We need to remember that it is obtained from a simple random sample. It should have no outliers. It should come from a population which is normally distributed. The sample size is large enough, greater than 30. And the sample values are independent of each other. And the sample size is less than 3% of the population size. Every question that I give you to do on a test is going to be able to be done. So you will be able to run the hypothesis test, but we will discuss really quick, hey, do these things work here in the examples today? Just like with proportions, we are going to start with creating our hypotheses. Remembering that we have three ways in which we can do them. The null is always an equals to statement, and then your three choices for the alternate are not equal to, less than, or greater than. Okay, we will also be given a level of significance to make sure that we do not make our error. We are going to use the p-value approach. So we will calculate our p-value. And if p is less than alpha, we will reject the null. If it is not, we do not reject the null. And lastly, we will state our conclusion. Process is the same regardless of what parameter we are testing. We are going to do the same thing every time. Biggest thing is when we're working with means, we need to remember that it should be drawn from a normal sample, or that we have a large enough sample. The biggest thing to remember is that because of the way that this process works, even if it's just slightly off from normal, a little bit askew, we will be okay to run our test. The biggest thing though is if we really have far outliers, we should not perform a hypothesis test. The mean height of American males is 176.3 centimeters. The height of the 44 male presidents, Washington through Trump. So just see here, Grover Cleveland was elected 2 times non-consecutively. So there have technically been 45 presidents of the United States, just so you know. Their height is a mean of 180.1 centimeters with a standard deviation of 7.1 centimeters. Treating the 44 presidents as a simple random sample, determine if there is evidence to suggest that U.S. presidents are taller than a typical American male. Use the alpha level of 0.05. We want to know if a U.S. president is taller than the normal American, who is 176.3 centimeters. We are talking about a mean here. So our hypothesis will have a mean symbol. So mu equals 176.3. We want to test that our presidents are greater than that. Our level of significance is 0.05. What we're going to do is use I will show StatCrunch here. How we're going to do that. Enter all of our data. We are working with means. Anytime we work with means, we are going to go to T-stats. We have one sample, and we have a summary of information. The mean of our sample of U.S. presidents is 180.6. 180.1, I'm sorry. The standard deviation that they told us for our sample was 7.1, and we sampled 44 of the presidents. We want to test Does our mean equal 176.3 or is it greater than 176.3? You can click this if you want. We're going to click compute. According to this, our p-value is 0.0005. All right, which is what is going to show on the next slide here. P-value is 0.0005. So how does that compare to our alpha? Well, 0.0005 compared to 0.5. Zeros are the same. 0 is smaller than 5. And when p is less than alpha, we reject the null. You're going to sing it in your head every time. If p is less than alpha, reject the null. You're going to sing it. It's going to get stuck in your head. Whether you believe me or not, it's going to get stuck in your head. If we can reject the null, then we have enough evidence to claim that U.S. presidents are, in fact, taller than the typical American male. The fun size Snicker bar is supposed to weigh 20 grams. Because the penalty for selling candy bars under the advertised weight is severe, the manufacturer calibrates the machine so that the mean weight is 20.1 grams. The quality control engineer at M&M Mars is concerned about the calibration. He obtains the random sample of 11 candy bars here, weighs them, and obtains the data that we have. Before I do anything, this is going to tell me, hey, I'm going to need to enter this data into StatCrunch here. Fun size Snicker bars, 1968, 1998, 2055, 2150, 266, 2065, 2036, 1974, 1956, 1961, and 2102. Oops, something did not. That should be 20.65. Okay. All right, so we have our data. Should the machine be shut down and calibrated? Because shutting down the plant is very expensive, he decides to conduct the test at the alpha of 0.01 level of significance. These candies are supposed to weigh 20 grams. The machine is set 20.1 just to be safe. So the way they have it set is it's set at 20.1 grams. And we want to find out, he's concerned about the calibration. It doesn't say, I think it's more or I think it's less. He just says he's concerned. That means, I don't know. I'm just trying to figure out, is it different? Am I off? One thing here, and I'll show you how to do this. The figure displays the normal probability plot and box plot. Basically, there's a visual way or a table way that you can double check, should I run this test? I can show you when we do that in StatCrunch here. Biggest thing is you could create a box plot. And as long as your box plot does not have any outliers, no points on the outside, I can run the test. So 2 ways to check: create a normal probability plot or check for outliers. We know that StatCrunch default puts those outliers in there if there are. So we could go and run the test. Just to show you again here, if I wanted to make my box plot just to check, graph box plot from my data. Okay, there are no outliers. Outliers will show as little dots outside. So I am able to run this test. The engineer wishes to determine whether Snickers have a mean weight of 20.1 grams or not. So our mean is set to be 20.1 grams. That is what our system has calibrated it to. And we're going to find out, are they not equal to 20.1 grams? We're going to use a two-tailed test, and our level of significance in this case is 0.01. We want to be very, very sure of our results. How do I then do this test in StatCrunch? Well, it is a means test. So anytime I do a means test, I go to T-stats, one sample. This time I have data. I'm going to select data, select my data, and enter my hypothesis. 20.1, not equal to. I can put my significance here. 0.01. And then I can do those other things here. So I can create my box plot within my test just to make sure that I did do this correctly. There are a few other tests in here. I want to see the other one we do. I want to say it's this one. So give me a second. I'm going to select that one and then I'll double check. Okay. Let me make this a little bit larger. Nope, that one wasn't it. Here's my box plot. I did select the right one for that. I think I want this one. I think it's the bottom two, box plot and QQ plot. Let's try that. So box plot. Yes. Okay, here's our normal plot. So we want to make sure that if we're looking at this, it looks like our data is spread about the same above and below the line. Here's the middle 0. You can see how many are below, above. It does look like we follow our correlation here, pretty strong correlation between this data. Really, it's a whole lot easier. Just look at the box plot if you want to double check that you can run the test. Then over here, here's our results. The p-value is 0.3226. 0.3226 rounds to 0.323. Comparing 0.3226 or 0.323 to 0.01. 3 is bigger than 1. P is greater than alpha. So we do not reject the null. You can look back here. Go back to our data set. It's going to give you the mean of our data. Our sample mean is 20.3. Our machine says it should be 20.1, 20.3. That's within our normal range there. So we are good. Keep our machine calibrated the way that it is. So there is not enough evidence to conclude that the Snickers have a mean weight different from the 20.1 grams at our level of significance. We should not shut down our machine. There is no reason for us to do any sort of tweaking of our machine. It is holding everything where we want it. So we got a few more examples here. In 1990, the mean height of women 20 years of age or older was 63.7 inches based on data obtained by the CDC Advanced Data Report, number 347. Suppose that a random sample of 45 women who are 20 years of age or older today results in a mean of 63.9 inches. State the appropriate null hypothesis to assess whether women are taller today. All right, well, what did we know? Our previous study said women were 63.7 inches. Oops, mean equals 63.7 inches. Which means our, oh gosh, not B. I'm not on B yet. Our alternate is wanting us to assess whether women are taller today. So are they greater than that 63.7 inches? Okay, now in this one, you're not going to actually run the test. Just a multiple part problem here. Suppose the p-value for this test is 0.35. So p-value equals 0.35. So that means about 35 out of 100 random samples would get our result of 63.9. So our sample was 63.9. 35 of 100 or 0.35 is not unusual. Remember, for there even to be a slight chance that we have enough data here, the p-value had to be smaller than 0.10. Remember that 0.10 was the highest we were going to go. Anything above that, we're not going to have significant evidence. It's not anywhere near unusual. So C then, write the conclusion. Well, if p-value is 0.35, that is clearly greater than our alpha of 0.10. So we do not have enough evidence to claim women are taller than 63.7 inches today. According to the American Time Use Survey, the typical American spends 154.8 minutes or 2.58 hours per day watching television. That is what we know. We have an average time spent on watching TV is 154.8 minutes. A survey of 50 internet users results in a mean time watching TV of 128.7 minutes with a standard deviation of 46.5 minutes. Conduct the appropriate test to determine if internet users spend less time watching. Our alternate, we know it's still 154.8, but we want to know if we have less than that based on our sample. So our sample was a size of 50 with a mean of 46 point, mean of, have that backwards. A mean of 128.7 and a standard deviation of 46.5. Alpha is 0.05. We're going to use our StatCrunch to get our p-value. Okay, anytime we have a mean test, we're going to go to a t-stat, one sample, and we have a summary. My sample mean was 128.7. My standard deviation was 46.5, and I sampled 50. My test value is 154.8. Oops, hit 7, not 8. And we are testing less than. So click compute. And here is my p-value. So my p-value 0.0001. If I compare that to 0.05, it is smaller than 0.05. If p is less than alpha, reject the null. So we're going to reject the null. And if we reject the null, we have enough evidence to claim the mean time spent watching TV for internet users is less than that 154.8 minutes. Calcium in rainwater. Calcium is essential to tree growth. In 1990, the concentration of calcium in precipitation in Chautauqua, New York, was 0.11 milligrams per liter. We were told it used to be 0.11. We have some data here. for 10 precipitation dates and they're following calcium level. A normal probability plot suggests the data could from a population that's normally distributed. Our box plot does not show any outliers, so that means we can run our test. Does the sample evidence suggest that calcium concentrates have changed since 1990? So changed means we want not equal to. We can't test greater or less, it's just not equal to. We know this is normal, that we can run our test. Calcium. What are our values? 0.0065. Nope, just 0.065. 0.087. 0.070. 0.262. 0.126. 0.183. 0.120. 0.234. 0.313. And 0.108. Stat, we're doing a t-stat, one sample. This time we have data on calcium. We are testing that our hypothesis is 0.11, and we want it to be different. Oh, that's right. So leave it there, not equal to 0.11. So let's see what we got. Our p-value is 0.122. Okay, if we're going to compare that to alpha of 0.05, 1 is bigger than 0, so p is greater than alpha. We do not reject the null. If we do not reject null, we do not have enough evidence to claim the calcium level in precipitation is different from at 0.11. I hope this is making sense. The same process for proportions as it is for means, as it's going to be for standard deviations. It's just a matter of remembering proportions. You go to proportion stats, means you go to t-stats, and when we get to standard deviations, we're going to go to variance stats. One more little thing I want to discuss here pretty quick is the difference between statistical and practical significance. So practical significance refers to the idea that while small differences between the statistic and parameter may be statistically significant, their difference may not be large enough to cause any sort of concern or be considered important. When we reject the null, we have statistical significance. The question then becomes, is it practical enough to make an impact? So let's take a look. According to the American Consumer Survey, the mean travel time to work in Collin County, Texas in 2017 was 29.3 minutes. The Department of Transportation reprogrammed all the traffic lights in Collin County in an attempt to reduce travel time. To determine if there is evidence that travel time has decreased as a result of the reprogramming, the Department of Transportation obtains a random sample of 2,500 commuters, records their travel time to work, and finds a sample mean of 29.0 minutes with a standard deviation of 8.5 minutes. Does this result suggest that the time has decreased at the 0.05 level of significance? First, we're going to run our test. this is what it was. That was our mean. Our mean was 29.3. And we want to now test, is it less than 29.3? Let me go back here so that I can see my data. We have a t-stat, one sample, and this time I have a summary. So my mean is 29.0, a standard deviation of 8.5, and I sample 2,500 people. We are testing that against 29.3, and I want to know if it is now less than. P-value 0.0389. The level of significance. P-value, P-value. Continued on the next slide is 0.0389. Use our technology to help us. We are going to compare 0.0389 to alpha, which is 0.05. 3 is smaller than 5. So P is less than alpha. We are going to reject the null. All right. Because the p-value is less than the level of significance, we reject the null. That means there is sufficient evidence at the 0.05 level of significance to conclude the mean travel time to work has in fact decreased. And so statistically, there is a difference here between 29.3 has now dropped to 29.0. That is statistically significant. So let's talk practical here though. While the difference between 29.0 minutes and 29.3 minutes is statistically significant, it has no practical meaning because 0.3 minutes is 18 seconds. If you save 18 seconds on your commute, are you really gonna care? Are you gonna notice? Is it gonna make you feel like you really saved a whole lot of time? No. Usually what happens here, and this is what happened in this one, we had a really, really large sample. When you get a really large sample, we are more likely to get that statistically significant result where it isn't really a practical significance. There are times where you can run a test, you will find that, hey, yeah, it really has changed. But does that change really matter? And that's the difference between statistical and practical. Just recap at this point, what we've done so far. If it is a proportion, we are following proportion stats, which follows the Z curve or the normal curve. When we work with a mean, we then go to a T distribution, T stats, which is a T distribution. Every single time, chapter 9, 10, and 11. Anytime you do a proportion, you're going to prop stats. Anytime you do a mean, you're going to T stats. Anytime you do a standard deviation, you're going to variance stats. Every single time. You get really comfortable with knowing where those tests are. This is the end of this section. We got one more where we're going to do some tests on standard deviations.